Alright guys, welcome to the area between two curves part 1. In this part we're going to be looking at vertical slices of finding the area in between two curves. So basically we're going to be looking at vertical rectangles and we're going to look at two curves and find the area between two curves on a set interval. So when we look at the definition, A and B is that set interval, where basically it's where the two functions intersect. Okay, and we're going to take the integration from a to b of f of x minus g of x dx. So it's important to know that a of b is the interval where f of x and g of x intersect. We need to make sure that we know which function is above the other, or on the upper boundary versus lower boundary when we talk about f of x subtracting g of x, and that's a hard part sometimes to determine. Okay, so we're going to look at 3 examples and we're going to go back and forth. The first example, I'm not going to give you A and B. The second example, I will give you A and B, and then the third one, we'll go back. And I think that's a good way to do it, so it mixes up a little bit. So a lot of things going on in example 1 here. First thing you should do is, after you read that example, find the area bounded by the graphs of y equals 3 minus x and y equals x squared minus 9. First thing that you should do is graph each function, and I've done that. The red function is our line, 3 minus x, and the quadratic is x squared minus 9. That's in blue. Okay, it's just a rough sketch. And when we take the area using vertical slices, what we're saying is that we're going to make vertical rectangles all the way through on the area of intersection of these two graphs. So I've drawn one rectangle in black there so you can see what we mean by vertical slicing. When I look at this function, I don't see the boundary. I don't see where I start, where I finish, from lower to upper bound. Where is that? So if it's not giving, if the interval a to b is not given, you have to find that. And we do that by setting the two functions equal to one another. So when I look at this, I want to see where they intersect. That means I have to find out where f of x equals g of x. So I set my two functions equal to one another, and I solve. I get everything to one side. It's a quadratic, so I bring all the terms over. I subtract 3x and add x, and I get this nice quadratic. When you solve a quadratic, you factor, if possible. It turns out we can factor. Two numbers that multiply to be negative 12 and add to be x are 4 and 3, and minus 3. And so x equals negative 4 and x equals 3. These two x's, that's our boundary. That's where, from 3 to negative 4, that's where we're looking. We're going to look at the area in between 3 and negative 4, because those are where the two functions are equal. They have the same output. So now I have to write my integral. So we can go from negative 4 to 3. And you can see that the upper function here is 3 minus x, and the lower function is going to be x squared minus 9 dx. And so what I've done here is I really just distribute the minus sign, the negative, and simplify. And then we get from negative 4 to 3 that integral of negative x squared minus x plus 12 dx. It's going to be on the top of our next slide, so we're not done yet. We still have to integrate to find this area. Now, this is the I rewrote the problem here, negative 4 to 3, and so now you have to integrate that, and the integration is here in brackets. Negative x squared becomes negative x cubed over 3, negative x becomes minus x squared over 2, and 12 becomes 12x. And notice here in red, negative 4 to 3, because that's where I have to evaluate the function and find that area. So what I do now is I plug both 3 and negative 4 into my integrated function. Here in the first set of brackets is when I plug in 3. Subtraction of when I plug negative 4 in. Be very careful when you simplify. Notice how negative 4 cubed over 3, and we have that minus sign, becomes positive 64 over 3. So be very careful when you simplify, because that can lead to some trouble. So I plugged in 3 and 4 both into my integrated function, and you can see here where I've simplified coming straight down. When I combine these two sums, and when I take the difference of the two, I end up getting 343 over 6. So when I add all these numbers together, subtract this sum, or this difference, I get 343 over 6. So that's the area between negative 4 and 3 of our two functions, the distance, the area between those two functions. So example 2, I'm going to give you the area, okay? And you still need to draw the figure because you got to figure out which figure is on top, okay? The upper boundary. So we have, find the area between y equals x and y equals x squared from 2 to 4. So I don't have to set the functions equal to each other. I can actually write my integral. Now when I look at the drawing here, I can see that x squared is going to be our top function and y equals 2x our bottom function. Okay, so x squared minus x dx, and I just integrate, and I have x cubed over 3 minus x squared over 2, and we're going from 2 to 4 on the given interval. So once I do that, I just integrate, which you can see here. We've integrated, now we're plugging 4 and 2 into our integrated function, and when I do that, I actually get it 38/3. So again, there's our interval from 2 to 4. I integrate my function, and I have to plug 4 and 2 back in to simplify. And don't forget, it's the top half, 4 goes in, minus the bottom half when you plug 2 in. So that's example 2 when you're given the interval. Final example, find the area between the parabola y equals 1 minus x and the line y equals 1 minus x squared. That should be switched. That's our line, that's our parabola. So find a and b, and f of x equals, we've got to find a and b. It's not given. We don't have a or b. Here's my two functions graph, and again I've drawn that vertical rectangle to kind of show you what's going on. When we find a and b, we set our two functions equal to one another. So there they are. And again, it's a quadratic. I actually bring the x squared piece over to make it positive and factor out an x. So x equals 0 and x equals 1 are my zeros here. So we're finding the area from 0 to 1. Okay? Now there's our integral from 0 to 1, but which function's on top? In this case, it's the blue function, the 1 minus x squared. And we're going to subtract off 1 minus x dx. So upon simplifying inside here, by distributing that minus sign, we get negative x squared plus x dx. I rewrote the function. What we're integrating from 0 to 1 of our function, negative x squared plus x dx. And now I have to integrate, which I do. And after I integrate, I plug in 1 and 0 into my integrated function, which you see here. And notice I'm subtracting off 0 on the second one, because when 0 goes in for x, you just get 0. So the answer is negative 1/3 plus 1/2. That's 1/6. Okay? So that's the area under two curves. So the area under our two curves, in this case, is 1/6 on the interval from 0 to 1. So in the next video lecture, you're going to see when we take horizontal slices, when we have rectangles that are horizontal. And we use that when we don't have one function on top of the other. Okay, so we'll see you for lecture number 2. Thanks.